So, uh, let's look at some of the approaches. We are sort of reviewing what I said last time, but I think it's worth doing so because I felt, at least to me, some parts I was just not in the mood on that day. So, um, some approaches: you insert a delay in the loop so that well, you do not try to access the data, fetch the data from the caches while it's being changed, but rather wait a bit longer until the data gets a bit more stable, or the someone else acquires it, and then you will not try to acquire it before. You can try spinning adaptively, and then there's the MCS lock that we will talk about more. So, atomic compare and swap. We said that this is an atomic uh, processor provided function or procedure that operates on a memory word that basically checks that the value of the memory word that you are spinning on has not changed from what you expect. So it's basically sort of spin. It's a function that provides you with a way to efficiently spin on just a memory word until someone changes that memory word for you. So it and the way it's used to actually build MCS locks is that you use it to build a queue of waiting threads, and waiting threads add themselves to the tail of the queue and basically spins on a flag in its queue entry. So it keeps spinning on some word that is designated for it. And of course, I mean, right here I talk about if it has changed, return an error, but then you can always have not in your if function or in your for function or in your while function. So have the exclamation mark basically. Then you add, once the thread adds itself to this tail of the queue, it spins on a flag in its queue entry, and this flag is changed by the other threads in the queue. And it's sort of a first in first out system, as it's mostly used inside the kernel. So what you have is that the thread before you will change that value for you so that you can get out of your loop and basically start working on the new data. So this is basically how an MCS lock is implemented. You maintain a list of threads waiting for that lock, and the front of the list holds the lock. So the first one in the queue holds the lock, and the last one in the thread is the newest one, and it's the last one to run basically. And yeah, you basically have an implementation or a pseudocode that looks like this. The lock is passed setting. So in the TCB, in the thread control block, you have basically a bool need to wait. This is basically the flag that you spin on. And the next, and you have also a TCB next. And once you basically quit, you try to change your next the TCB the bool need to wait in the TCB of the next thread to you. Okay, so and if need to wait is false, then you run. If need to wait is true, then you basically need to block. And this is how the operation would look like. So you'll have in the beginning a tail nil. You'll have nothing in that queue, nothing in that thread, and then thread A joins, and it doesn't have to wait. So need to wait is false. And then a thread B joins, and since thread A is still running, then it has to wait. So its true is false, and it actually changes the value in B. Sorry, in A, the next value to be B, and then C joins, and it has to wait for B now, and so on. And you might even have a very long list of threads, and this is mostly used inside the kernel. The other way to handle kernel locks is to use read copy update. It's I mean this is stuff that you mostly do not use in your day-to-day locking, but it's mostly for very high performance systems, and they're used in the Java virtual machine, for example, in some of the compilers and in the operating system. So more towards the systems programming side rather than the the day-to-day programming. And you can also think of them as something that you will use if you go and work for Google or Facebook or one of the larger companies that have high infrastructures and you're working as a back-end engineer, then yes, this will be also something that you will be looking at. So read, copy, update, we sort of talked about them a bit also last time. And the goal is to have very fast reads to share data and restricted updates, and the updates are basically, or the writes are slower. You can have multiple concurrent versions of the same data at the same time, and well, you need to handle that because what you have is that you have no locks on reading, but you have locks on writing basically, and the locks on writing stops multiple threads to write concurrently, but does not stop other threads to read the old data at the same time. The way it works is that the writer basically takes a copy of the data, operates on it, and then posts a pointer to the new data value somewhere. Somewhere is something that is predefined, of course, and basically in that place all threads can see that now there is a new version of the data that is available. But since some of the data starts the read maybe before you start the write, so let's suppose that you have a write, the one at the bottom that's called write new, that starts while a couple of threads are actually reading. Okay, so you have two threads on top that read and finish before the write even finishes. So they will operate on the new on the old data, while some threads actually start before the new write is completed. And in that case, these threads can end up reading either the old data or the new data, because the new data will be finished at the update is published line. And then if you have the data by then and you're rereading, because the thread might be rereading the same value multiple times, then the thread might end up with multiple versions of the value. And then it's up to the thread to operate on the old or the new value. And well, then you have a grace period for all threads to finish what they are doing with the old value before you completely override the old value. Any new thread that starts after the update is published will read the new value only, will not read the old value, because that just doesn't make sense. And then basically you have a grace period after which all old values are flushed. And if you have something that is running for longer, then that will have to update itself. So if you have a thread that runs for longer than the grace period, you should know that, well, you might be subject to reading multiple values at the same time. So you have to handle multiple different value reads. And then when the grace period ends, the delete command is issued to the old value. So the way that read copy update implementation is that readers disable interrupts on entry, and they guaranteed to complete the critical section before the grace period finishes. And there are no read or write locks basically. And since you're disabling the interrupts, that means that you have to run pretty fast, so that it's used in the kernel. It's not used outside of the kernel for this reason, because you basically disable interrupts. And Also, one of the reasons that you disable interrupts while reading is that you do not want even more uncertainty by having an interrupt that rewrites some of the values that you're reading, and then it's just a mess of inconsistencies. The writer, on the other hand, needs to actually run, so acquire the lock, compute the new data structure, publish the new version, release the lock for others to write, but still the writer is not done. It needs to wait for the grace period before it's actually done. And then after the grace period, the writer has to delete the old data, and then the writer is now considered done. And you can see here that you can have, this is basically a multi-threaded version with concurrent reads and writes. So you can see that line 1 has 3 reads, line 2 has 2 reads, line 3 has 2 reads, line 4 has write, line 5 has a write, and line 6 has a write. And you see that on the first 2 lines, they run concurrently, actually the first 3. So you acquire read lock, which doesn't mean anything, and you start reading the values concurrently, it's no problem, and you unlock. And here, locking and unlocking is just releasing the releasing the interrupts and acquiring and stopping the interrupts. Then the write, you have a write that starts, it acquires a write lock, it publishes value 1, and then it has a write unlock, and then it synchronizes. Okay, and the synchronization is basically the cleanup and the garbage collection and so on. On the 5th line, there's a writer that is trying to acquire the write lock. It is not able to acquire the write lock until on line 4 the writer is done, and then you basically have you start publishing version 2 at that point. And on the last line, again, another writer tries to acquire the lock. It's not able to acquire the lock until the write unlock is done, and then a new value is synchronized.